Yes, thank you, Mr. Chairman, and good afternoon, ladies and gentlemen. This work was carried out by Per Madsen and Just Jensen from Aarhus University in collaboration with Jukka Pöysi from Faber Coop Finland, with Jørn Pettersen from the Knowledge Center of Agriculture Denmark, and myself and Nordic Genetic Evaluation. And I think Per Madsen did make by far the largest contribution to this work, and he was also preparing this presentation. But due to health problems with his back, he could not come to Cork, and so he was asking me whether I could lead you through his presentation, and this I will try now. So there were two objectives in this work. One was to develop, implement, and test a simple multivariate method for detection of extreme outliers before data used in genetic evaluations. And then the second objective was test the effect of deleting extreme outliers from genetic evaluation. So why multivariate outlier detection is important? Let's assume we would have data with triplets of highly correlated observations, like given here with this matrix. And let's assume we would have one set of this triplet where each observation is deviating about 2 standard deviations from its expectation, but one is even deviating in the opposite direction. So thinking we would apply univariate outlier detection, we would consider that all these 3 observations are very well acceptable. But if we think now we compute the conditional distribution of variable x3 on given the other 2 observations, then we will find out that the observation x3 would deviate actually more than 14 standard deviations from its conditional expectation. And so we really see here we have a multivariate outlier here. So to demonstrate the idea Per Madsen is suggesting, let's consider now a simple multi-trait linear model with variance structures, which is very well known to you. And now if we organize our data in a way that we have records with correlated observations like milk, protein, and fat, then we can calculate for one record with these correlated traits a deviation from its expectation. So here it's indicated by the vector d. And we also can show what is then the variance of this vector, which would be the variance of the observations itself, plus then a part of the variance which is related to the standard error associated with estimating the fixed effects. So standard methods for detection of multivariate outliers are based many times on this Mahalanobis distance. And this is the square root of a standardized dot product of these deviations, where the D is the covariance matrix of the deviation vector. And under the assumption that this D vector is multivariate normal distributed, then it can be shown that the square of this Mahalanobis distance is approximately chi-square distributed. Per is now suggesting a few approximations that we can calculate this Mahalanobis distance. And the first one is we face here the problem that we cannot invert the coefficient matrix. So he suggests that it is reasonable to use just the variance due to the phenotypic observations as an approximation for the D matrix. And then he has a second approximation, and this is by partitioning the fixed effects vector in 2 parts. In one part with fixed effects, which I estimated with a high accuracy, like a lactation curve. And the second part would contain, for instance, Hurd-Teste effect. And now by doing so, he can use for the B1 solutions from a previous BLAP run and keeping B2 to be to be set 0. So the B2 should be actually 0 here. And this saves us for doing an additional blob run. Then when we define that S is a vector of valuated function to compute the phenotypic standard deviation of these observed traits in record I, then we have everything ready that we can get first an approximated expectation for these observations, and we can also scale then the D matrix by the vector S to account for this, that we are working on an approximated D matrix. And with this, we're able to calculate the Mahalanobis distance squared. Garrett in 1986 proposed to use a chi-square plot for detecting a cutoff point to judge whether there is an outlier or not. And the idea of this chi-square plot is that if you plot the M2s of each record, or this empirical distribution of the M2s against the chi-square distribution, then in the case that all the data is multivariate normal distributed, then you would obtain a straight line. And if this is not the case, then you would see a break in the tail of the distribution. So the method has been applied to Jersey evaluation data with about 10 million test records from over 500,000 Jersey cows, and one record consisted of milk, protein, and fat yield observation. And we applied this NAV Jersey test model to test the approach. EBVs were expressed in indices with a mean of 100 and a standard deviation of 10. Here you can see the results from the chi-square plot. And if you now focus on the upper left plot, there you would have on the, it's difficult to see on the x-axis, the M2 or M square value for each record, and on the y-axis you would have then the corresponding chi-square value. And as you can see here, when the M square value is larger getting than 30 or 40, then you see that the tail is really deviating strongly from a linear curve. All the other three plots show you just if you move then the cutoff point towards the left side, you will see that the remaining, or the plots for the remaining observations is approaching more and more a straight line. So we were estimating breeding values for different situations to test this approach. The first one was on raw data, so there was nothing deleted, and then there were 3 different situations where we deleted on a cutoff point M squared larger than 100, larger than 60, or larger than 30. And like larger than 30 was the most strict criteria, and as you can see in the bottom right corner, there were then about less than 2 promille of the data deleted. We looked at predictive ability to assess the effect of deleting these outliers, and we did this by calculating the correlations between EBVs from a full data set and a reduced data set, and we were looking on cows which got from the reduced data set a parental average, and from the full data set their breeding value based on own observations. So let's look now on this situation where we were using all the data, and here you can see now from the first column that the correlations between parent average and later EBV was between 0.55 to 0.59 for milk, protein, and fat for all the cows. But then for the other 3 columns, there you see then these groups of cows where an outlier has been detected but not deleted. And there you can see that the correlations were clear, smaller. And now let's concentrate on this group of cows where at least one outlier was detected by this cutoff point M square larger than 30. As you can see, raw data column has the same values as I have presented in the previous slides. Then when we go to the situation MD100 and MD60, we do not see much improvement. What was clear, because this was only related to a few cows where outliers were deleted. But then with the last option, deleting the outliers of all these 3,500 cows, then you can see that for fat and protein yield, the correlation clearly improved, maybe not that pronounced for milk yield. So there's a clear improvement when we delete these outliers in terms of accuracy. We also look then how this deleting of outlier affects on the indices of all the bulls. And as you see in the middle, the majority of the bulls did not show any change in the breeding value indices, or not more than ±1 index point. But for some bulls, there were larger changes observed. And now the same for cows. In cows, you can see again the majority, there is no change in the EBV, or not more than +1 index point. But anyway, we had then some hundreds of cows where the indices is changed over half a standard deviation, so very significant. And these were cows where we really could detect also an outlier in their data. We also carried out the IBOM3 test validation on all these 4 different situations, and what we found here that there was hardly any effect when deleting the outliers. So in conclusion, we can say that this method is very easy to implement. Anyway, the thing is that we need to determine a suitable cutoff point, and what Per suggests here, that actually using the data sets that is needed for making interpol 3 validation test is very suitable, because there you can do this accessing the correlations between for predictive ability. And then as a very last conclusion is we could see when applying this method the accuracy of breeding values of those cows where we could detect an outlier and delete really increased. Thank you very much.